Now let's move on to the Chem 30 stuff. In order to put this into context, I want you to always think on every question in this entire unit, there's going to be two questions you need to ask yourself. Number one, is this a chemical or a temperature change? If it's a temperature change, then we just learned or reviewed the Q equals mc delta T formula. If it's only a temperature change, that's your formula. If it's a chemical change, though, you can't use that formula. You have to use a different one. So that's your first question. On every question you do for this whole unit, chemical change or temperature change. The second question is, am I losing or gaining energy or heat? Those are interchangeable in this unit. So is this a loss or a gain of heat or energy? And that's going to come to play, especially in our chemical reactions, when we start looking at, is this endothermic or exothermic? The formulas will give you the amount of energy, the number, but it may not tell you whether it's being lost or whether it's being gained. So you're going to have to ask yourself that question. Okay. Now, in the notes, you've got some information there about chemical change. So it involves a change in the chemicals, what they actually are. Remember, temperature change didn't. You start with water, you end with water. In a chemical change, though, you change from something to something else. So the example partway down the page there, you've got hydrogen and oxygen becoming water. That's a new chemical compound. That is a chemical change. But every time you have a chemical change, let's use that example. So if we use that example, I have H2 plus O2 becomes H2O, and we need to balance that. But in order to do that, if we think about it, remember that H2 is two H's stuck together, O2 is two oxygens double bonded together, and H2O looks like this. So in order to change this around, I have to break all of those bonds. These have to break because there's no oxygens over here in the product side in water. There's no oxygens bonded to oxygen. There's no hydrogens bonded to hydrogen. So these bonds have to break. And in your notes, you'll notice on point 2 there that breaking bonds between atoms requires energy input. So I'm putting energy in to break that bond, and I'm putting energy in here to break that bond. When we form new bonds like over here, the formation of those new bonds releases energy. So when we form new bonds, it releases energy. So the difference between when a reaction is endothermic or exothermic isn't meaning it only releases or it only absorbs. It's a matter of how much. So I'll tell you this one is an exothermic reaction, but it's doing both, right? Technically over here on the reactant side, it is absorbing energy, and on the product side, it's releasing energy. So the reason is because over here, it's absorbing, it's gaining a little bit of energy, but over here, it's releasing a lot of energy. So the overall is that it's lost more energy than it's gained. Don't worry about those arrows, the up and down that I just drew. It's just a way of showing it. We're not going to represent it that way. But that's just a way of showing more energy is being released from this side, like this, kind of like our other diagram that we did. And only a little bit is being absorbed on this side. So overall, it's a more exothermic reaction. Okay, when we're doing this in our problems, if you were doing a calculation and you found out that it was an exothermic reaction, we make that a negative number to show that that was energy being lost. Now, this is not necessarily a mathematical negative because it's not going to show up in our calculations necessarily. It's a number you have to put in just as a way of saying this is exothermic. If it's endothermic, it's going to be a positive number. But you'll have to put those negatives and positives in. If you try to do your calculations with those numbers in, you're going to get things like negative mass and things like that are confusing. So we're going to actually leave the positives and the negatives out of our calculations until the very end. And you'll put them back in, not because the math told you to do it, but because you knew it was either exothermic, so it's negative, or you knew it's endothermic, so it's positive. And we're going to run into this new thing called delta RHM. We're not going to worry about the R for today, so don't stress about that right now. But that's a new thing we're going to talk about that has to do with enthalpy per mole of a substance. So this overall exo or endo is measured in delta H, which we call enthalpy, which is just a change in potential energy. And this is saying change in potential energy per mole. So here's an example I'd like to give. Let's say you had a campfire and you put 3 logs on that campfire, had them nice and stacked up sitting here, and then you start this on fire and now it's burning. Okay, so overall, if you just want to know how much heat is coming off this energy, delta H would be your total energy. Just how much energy is the whole thing releasing? What's the change in potential energy? But let's say I wanted to break it down and be more precise. I want to say, well, how much energy did I get per log on the fire? So if I take my delta H and divide it by 3, that would be my energy per log. And that's kind of what delta HM is, except instead of using logs, we're going to use moles. So it's going to be the amount of energy, or kilojoules or joules per mole of a substance being burned. But if you kind of keep that in mind, hopefully that'll help you keep delta H and delta HM separate. That those two things, this one is a total energy, this one here, and this one is just per mole. All right, let's look at the formula now. So the formula here you'll use for chemical change, is delta H, which we just said was enthalpy change, which is our change in potential energy, and it's going to be measured in either joules or kilojoules, most often kilojoules, but some basic unit of that. And then we have N, which is number of moles, and delta HM, which is our molar enthalpy, which is going to be in joules per mole or kilojoules per mole. And just like before, remember that these units are going to have to be the same, otherwise in your math they're not going to cancel out and it may cause you some problems. So if we go ahead and try the example problem here, we have what's the molar, and if the molar enthalpy of combustion is negative, remember that negative just means exothermic, 2043.9 kilojoules per mole, then determine the enthalpy change of 10 grams of propane burning in a camp stove. So remember the two questions: is this temperature, chemical change, or both? So when I read this problem, they're not, even though I know there will be a temperature change, they're not asking me about that. They're just asking me about the chemical change. So my formula is going to be delta H equals N delta HM. And I'm going to make one small change to this formula because I know that N, if you think back to Science 10 and Chem 20, is equal to the mass over the molar mass, that I can move between moles and mass by using this formula. If I know that, and because the question gave me the 10 grams, I'm going to say delta H is equal to mass over molar mass, just substituting N for this, delta HM. Because they gave me a mass. They gave me 10.0 grams. Now, in order to do this, I have to find big M, capital M. I need to know the molar mass of propane. So propane, remember from organic unit, prop is 3, so that's C3H8. So if you look at your data booklet, the molar mass of carbon times 3 plus the molar mass of hydrogen times 8 should give you 44.11 grams per mole. So looking so far, this gram and this gram are going to cancel, and I'm going to be left with this per mole on the bottom so far. Now I have to times that by the delta HM, which in this case is negative 2043.9 kilojoules per mole. I guess I should write that the same way that I did before, just to be consistent, per mole. And because I have a per mole on top and a per mole on the bottom, they're going to cancel. Now I do want you to put a note here though and cross this out, that negative, and write down in your notes, don't put this here. Because remember that negative doesn't necessarily mean mathematical negative, although sometimes it'll work, in other cases it will mess you up. I want you to get into the habit of don't put those negatives in there at all. Just take the number value, do your calculation out, and then if you need to, because it's exothermic, put it back in at the end if it's needed. So if you look at this math, if you were to calculate this out, you would need to go 10 divided by 44.11 and then times 2043.9. And you should end up with 463, because this number right here only has 3 significant digits. So 463, and the units that are left are here, the only ones we didn't cancel. So this is going to be in kilojoules. Because this is exothermic, in the end, I'm going to have to put that number or that sign back in to say that that was a loss of energy. So we're going to put this in here because it's exothermic. Okay, so I know that this is a bunch to learn and it's some new formulas and a new kind of way of thinking, but you've got a bunch of problems to practice this on. Just remember, if it's a temperature change, to use the Q formula. If it's a chemical change, use the delta H formula. And you've got 3 pages of problems here. And then on the last page on 1-6 is your answers. So if you come across anything that you're not understanding why you're getting something wrong or you're having trouble with, then send me a message and I'll help you work through it.